Okay, finding the center of mass and center of mass calculations, non-calculus. All right. Well, the meaning of the center of mass will become more obvious as we get deeper into this, but because of the way the gravitational force works, particularly near large bodies like the Earth, the center of mass and the center of gravity are the same location, which means you can effectively balance an object at its center of mass. It's a useful point to know how to find. The way you would want to think about finding it is the center of mass is a weighted average. So you've calculated weighted averages at some point in your life, I would imagine, especially if you're trying to calculate your own scores in a class. You'd take the weighting for the score times what you got on that part, plus the weighting times the next part, plus the weighting times the next part, and so on, and then divide by the sum of all the weightings. Like if it's 5% quiz, 10% homework, 20% lab, you'd multiply by those values and divide by the total at the end. So the way you would find the center of mass in a particular coordinate like x, which I will call x with a bar on top, is just equal to mass 1 times position 1, where the masses are the weighting, plus mass 2 times position 2 plus mass 3 times position 3, and so on. So m1x1 plus m2x2 plus m3x3 divided by the total mass. If you extend this idea to as many particles as you want, you'd write it as the summation from I equals 1 to however many things of m sub I times x sub I divided by the sum from I equals 1 to n of m sub I. So all the masses added together on the bottom. This handles a single direction. You could write the exact same kind of equation out for the x and the y directions as well, but it might be best, since we're really into vectors in this class, to just write the r vector with a bar on top for the center of mass, and it would be a summation from I equals 1 to n of m sub I times r vector sub I, all over a sum from I equals 1 to n over m sub I. Okay, this actually has wider applicability outside of simply dealing with particles, which is actually the first way we're going to use it. The earliest examples are going to be just particles at particular points, and then we add up the masses times their locations and divide by the total mass, and we get our center of mass. You can also use this with extended shapes whose centers of mass you happen to know. For instance, I'm going to give just a very quick example. If you had two very skinny rods, one set up on the top of the other at right angles, each with a length L and a mass M. We know where the centers of masses for those would be. If they're of uniform density, they'd be at the geometric centers. So we could just say, well, this first one, all the mass is concentrated at a point that is all the way over on one side and at a height of L over 2. So we could say that coordinate is 0, L over 2. The second one, it would be located at the full height L, but it would be located at a distance L over 2 off to the side. We could now take these as two individual masses and use our method from above, treating them as point masses, to find the center of mass of these two rods together. In this case, if we were finding the horizontal center of mass, we'd have m times 0 plus L over 2 times m, all divided by 2m, so we'd get L over 4 in the x-coordinate. And we could do much the same thing in the y-coordinate. We'd have L over 2 times m plus L times m, all over 2m. The m will cancel out. We get, oh gosh, what is that? 3/2, so 3/4 L. And that gives us the y location of the center of mass. This is something you should know how to do. It is a way that you can shortcut circumstances if there are simple shapes that you already know the centers of mass for. Strongly recommended that you understand how you can use this as an approximation to get fast results for extended shapes. Okay. Next time we'll be coming back and talking about what to do if you have to use calculus, if it's an extended shape that isn't something simple to figure out. It's a bit more interesting, and it's one of the first times we'll be applying some of the ideas you may have seen in a calculus worksheet if you're in one of my classes, where that is a lab we do. But for now, we're going to stop there. This is how you calculate center of mass. Remember the formula. It's a super easy one to recall because it really is just the equation of a weighted average. I say that like it's super easy. Not everyone notices that, but once you do, it becomes really easy to understand what's going on. All right, so I'll see you in the next one.